A-level mechanics, statics, turning moments. Let's consider the turning moments of a force. Now often we use a force to move an object along. However, sometimes we use a force to rotate an object. For example, if an object such as a door or a gate is hinged, then applying a force to it causes it to rotate around the hinge rather than move off in a straight line. In this case, it's quite important where we apply the force. If the force is applied near the hinge, the gate is difficult to open. If the force is applied to the other end of the gate, it'll be easier to open. We see this when trying to open stiff nuts and bolts. If a spanner is used to undo a nut, then the longer the spanner, the easier it is to open the nut. The shorter the spanner, the harder it is to open the nut. So we introduce the idea of a turning moment of a force. When a force is applied to a body that is fixed at a point about which it can rotate, then as long as the force does not pass through the pivot point, the force will generate a turning moment. Then we have the turning moment is equal to the force times the perpendicular distance of the force from the pivot. If we look at the diagram, in this case the turning moment of the force F about the point O is F times D, where D is the perpendicular distance of F from O. Now let's consider a force F acting at a point A some distance from another point O. And let's suppose the angle between OA and the force F is theta. In general, if a force is applied to an object A, then the turning moment of the force about a point O is given by the turning moment equals F times OA times the sine of the angle theta, where theta is the angle between the line OA and the force F. Note, OA sine theta is the perpendicular distance. Let's look at an example, example 1. Once there was a toy that consisted of a balance with two long arms with pegs evenly distributed along each arm, numbered 1 to 10. Rings were then added to both sides. The arms would only balance if the sum of the numbers on each side were equal. This was a way for children to practice adding up numbers. In the example here, consider the turning moments of the rings. Let each ring have mass m and let the distance between the pegs be d. In this case, the rings on the left try to turn the beam anti-clockwise, the rings to the right turn it clockwise. Now the force down on each ring is mg, so the anti-clockwise turning moment, ACTM, is equal to mg times 8d plus mg times 5d plus mg times 2d, which is 15 mgd. And the clockwise turning moments, that is the rings on the right-hand side, have a turning moment of mg times 6d plus mg times 9d, which is also 15 mgd. So we see, for the beam to be in equilibrium, we must have the sum of the clockwise turning moments equals the sum of the anti-clockwise turning moments. Let's look at another example, example 2. A uniform plank 10 meters long is supported 1 meter from each end. The plank has mass 8 kilograms and a boy of 48 kilograms stands on it 2 meters from one end. Find the reaction forces on the plank at the two supports. Well, to solve this, we need to draw a diagram and mark in the forces on the plank. Well, to begin with, we have the weight of the plank, which is 8g, which acts in the middle of the plank, so that is 4 meters from A. Then we have the weight of the boy, that's 48g, and acts 2 meters from the end of the plank, so that is 1 meter from A. We also have a reaction at A which acts vertically upwards. We can call that P. And we have a reaction at B which acts vertically upwards. We can call that Q. Q is 8 meters from A. If we resolve vertically, we have P plus Q equals 48G plus 8G, so P plus Q is 56G. If we resolve horizontally, we just get 0 equals 0, which doesn't help us at all. So we need another equation. Well, we can take moments about A. Now the anti-clockwise turning moment is Q times the perpendicular distance of B from A, which is 8. So it's Q times 8. And the clockwise turning moments are 48G times 1 metre plus 8G times 4 metres. So we have 8Q equals 48G plus 32G, or 8Q is equal to 80G, and so Q is 10G newtons. Now we know that P plus Q is 48G, and so P is 38G newtons. So we have P is equal to 38G, which is 372.4 newtons, and Q is 10G, which is 98 newtons. Example 3. A plank of mass 12 kilograms and length 5 meters rests on two supports. They are 0.5 meters and 3.5 meters from one end. In part A, we're asked, a child of mass 30 kilograms wants to walk to the other end. How far can she walk past B before the plank tips? Well, to solve this, we'll assume that she walks X meters past B. On the point of tipping, mark in the forces. Now the first force is the girl's weight, and that's 30G. There's also the weight of the plank, that's 12G. There's a normal reaction at B, but there's no normal reaction at A because the plank is on the point of tipping. If we take moments about B, the distance of the weight of the plank from B is 1 metre, and the distance of the girl from B is X meters. So, taking moments about B, we've got 30G times X equals 12G times 1. So 30X equals 12, or X is equal to 12 divided by 30, which is 0.4. So she can walk 0.4 metres or 40 centimetres past B. Now in part B it asks, if a rock is placed on the plank at A, what mass would it need to be for her to reach the end? Well, let the rock have a mass m kilograms. On the point of tipping, mark in the forces. We've got the weight of the girl, which is 30G. We've got the weight of the rock, which is mg. And we've got the weight of the plank, which is 12G. We have a normal reaction at B, but we don't have a normal reaction at A because the plank is on the point of tipping. Now, the rock is 3 metres from B, the girl is 1.5 metres from B, and the centre of the plank is 1 metre from B. So, taking moments about B, we have mg times 3 plus 12g times 1 equals 30g times 1.5, which gives us 3m equals 45 minus 12, which is 33. So m is 11. So the rock must have a mass of at least 11 kilograms. Example 4. A ladder of mass 6 kilograms is 4 meters long and leans against a smooth wall, making an angle of 66 degrees with the ground. In part A, we're asked to find the normal reaction at the wall. Well, to do this, we draw a diagram and mark in the forces. The first force is the weight of the ladder. That acts halfway up the ladder, 2 meters up the ladder, and is 6g vertically downwards. And then we have a normal reaction of the wall against the ladder. That is a force perpendicular to the wall. We can call it P. We have a normal reaction at the ground. We can call it R. That is a force acting vertically upwards. And there is a frictional force at the base of the ladder, and that is towards the wall, preventing the ladder from sliding away from the wall. Now, if we take moments about the base of the ladder, we can see that P makes an angle of 66 degrees with the ladder, and the weight 6G makes an angle of 24 degrees with the ladder. So we have P times 4 sine 66 equals 6G times 2 sine 24, or P equals 6G times 2 sine 24 over 4 sine 66 degrees, which works out P is 1.336 G, or P is equal to 13.089 newtons. In part B, we're asked to find the frictional force with the ground. If we resolve horizontally, we have F is equal to P, and so F is also 13.089 newtons. In part C, we're asked to find the normal reaction at the ground. If we resolve vertically, we have R is equal to 6G, which is 58.8 newtons. And so we have the normal reaction at the ground is 58.8 newtons, and the normal reaction at the wall and the frictional force are both 13.1 newtons. Now we have quite a useful result when exactly three forces act on a body in equilibrium. If we have exactly three forces in equilibrium acting on a body, then the three forces are concurrent. That means they all pass through the same point. In the diagram, suppose we have three forces acting at A, B, and C. Now extend the lines of the forces back until they meet each other. Suppose they do not meet at the same point. Then mark the intersection of the lines through A and B as D. Now, taking moments about D, we see that only C has a turning moment about D, and there is no other force to balance it. This situation could not be in equilibrium, so the line through C must pass through D, and they will all be concurrent. Example 5. A drawbridge to a castle is a uniform plank of length 4 metres and mass 600 kilograms. It is hinged at one end, and the other is supported by a light cable. The cable is attached to the castle wall 3 metres above the hinge. In part A, we're asked to calculate the tension in the cable. Well, to solve this, draw the forces acting on the drawbridge. First of all, there's the weight of the drawbridge, which is 600 G, acting in the middle of the drawbridge. So that is 2 metres from the hinge. Then there's the tension in the cable, we can mark it T, and there's a reaction at the hinge, we can mark that R. To obtain an equation only involving the unknown T, take moments about the hinge A. Let the angle between the plank and the cable be theta. Taking the anti-clockwise turning moments about A, we get T times 4 sine theta, and that's equal to the clockwise turning moment, 600 G times 2. Now the triangle ABC is a right-angled triangle with sides 3 metres and 4 metres. So the hypotenuse is 5 metres. That's Pythagoras' theorem. So the sine of theta is 3 over 5, or 0.6. So we have T times 4 times 0.6 equals 600 G times 2, which can be rearranged as T is equal to 1200 times G over 2.4, which is 500 G, or 4,900 newtons. So the tension is 4,900 newtons. Now in part B we're asked to calculate the magnitude and direction of the reaction force from the hinge to the drawbridge. Now, we can find R by resolving vertically and horizontally. However, if there are exactly three forces acting on a body in equilibrium, then they're concurrent. So, if we extend the weight upwards and we extend R, we find that T, R and the weight all go through the same point, which we'll call D. Since the 600G force acts in the middle of the plank, the triangle ABD is isosceles. So R makes an angle theta with the drawbridge, and we know sine theta is 0.6. So theta is 36.87 degrees. And if we resolve horizontally, we get R cos theta equals T cos theta. In other words, R equals T, which is 500G or 4,900 newtons, and so R is 4,900 newtons at an angle of 36.9 degrees to the drawbridge.